Hello, it's 1 p.m. Eastern Time, and wherever you are in the world, I'd like to welcome you to the first ever NULCA webinar conducted by Sensors and Software. Special thanks to Ron Peterson at NULCA for initiating this. My name is Troy D'Souza, and I'm the training manager at Sensors and Software. Sensors and Software is a manufacturer of GPR equipment, which are used in a variety of applications. By far, the biggest application of GPR worldwide is locating utilities. However, sometimes GPR's capabilities are oversold or misunderstood. The goal of this webinar is to discuss what GPR can and cannot do to help you ensure that it's used properly on projects to maximize the results. If you have any questions, please write them down and submit them at the end of this webinar, and I will answer them at that time. The webinar itself should take about 30 minutes, followed by some Q&A. So the learning objectives for today are as follows. Understand what affects GPR penetration. Discover ways to improve your results in challenging ground conditions. As many of you use traditional EM equipment, we will learn how GPR complements these pipe and cable locators. And finally, we'll review some case study examples that contain some insightful data. So let's start with a quick review of the basics. Now this animation may appear a little bit choppy for some of you, so I'm going to let it play a few times so that you kind of get the basic idea. GPR is a technology that uses radio waves to locate objects in the subsurface. We do this by pushing the GPR system along the surface and collecting data from reflections in the ground. GPR waves do not reflect off changes in density, as many incorrectly believe. It reflects off changes in material properties, specifically changes in dielectric constant. A PVC pipe has a different dielectric constant than the surrounding clay soil, for example. Similarly, a layer of sand will have a different dielectric constant than a layer of bedrock. And both of these interfaces can be detected by the GPR. When we cross an object perpendicularly, we get a hyperbola on the screen. A hyperbola forms as the GPR passes over top of the object. The object is located at the peak of the hyperbola. So this is pretty easy, right? But as many of you know, targets do not always show up this clearly. There are a few factors that determine whether or not GPR will find an object. The biggest limitation of GPR is the depth of penetration. Penetration depends on the electrical conductivity of the soil. The higher the electrical conductivity, the faster the soil will absorb the radio signal and prevent deeper penetration. So let me set the stage before I play this animation. The following animation was created using a GPR simulation software, which shows a pipe, the same composition and the same depth, buried in 3 different soils. Okay. So let's start off. On the left, we see a soil with low electrical conductivity. An example of this soil would be sandy or gravelly soils. The amount of GPR signal that reflects and reaches the surface is high. This object is easy to detect. In the middle, the soil has a moderate to high electrical conductivity. An example would be silty soil. The GPR signal is greatly absorbed, but there's still a small amount that reaches the surface. The hyperbola from this object will be weak, but still detectable by the GPR. And finally, on the right, we see the situation where the electrical conductivity is so high that the GPR energy cannot travel down to the utility, reflect, and return to the surface before being absorbed. This happens in clay-rich soils. So in this particular simulation, that utility is invisible to the GPR. Simple as that. So for those of you that live in the US, There is a soil suitability map produced by the U.S. Department of Agriculture. Some of you are probably already familiar with this. By visiting the website shown over here, you can zoom in on any state. In general, areas in green are good for GPR, where areas in orangey red will limit penetration. Keep in mind, this is a very good resource that gives you an idea of how GPR should perform in a region. Of course, keep in mind that urban areas that have been dug up, disturbed, or backfilled may have different results, so take it with a grain of salt. Another factor is the material composition of the pipe. Metallic pipes reflect better than non-metallic pipes. Having said that, a major advantage of GPR is the ability to detect non-metallic utilities. In the example below, there are two pipes buried at the same depth with the same diameter. Obviously, the one on the left is stronger because it's metallic, but the one on the right is still detectable, albeit weaker. And finally, the size of the pipe is also a factor. Larger diameter pipes reflect more energy and show up stronger. The deeper you go, the larger the pipe must be for it to be detectable. There is a rough rule of thumb that says for every 24 inches in depth, you should add 1 inch in diameter for it to be detectable. This 24-to-1 rule is just an approximation, but it should tell you that a 1-inch diameter pipe buried at about 7 feet deep will be next to impossible to locate with GPR. Another factor to consider is the center frequency of the GPR system you are using. In GPR, there is a trade-off between depth penetration and spatial resolution. Spatial resolution has to do with detecting small objects as well as differentiating one object from another one close by. Lower frequencies will see deeper in the ground, whereas higher frequencies will have better resolution. In the example shown below, data was collected over the same area with 3 different frequencies. Okay, so we're just going to look at the first frequency for now. The objects were buried in sand, which is a good medium for GPR, allowing us to see relatively deep and with good clarity. So the first frequency we're looking at is a 250 megahertz base system, and this is common among many utility locators. And our focus is on these 5 strong hyperbolas that we see about halfway down the screen. Now, if you are looking for shallower utilities, for example, fiber optics, you could use a 500 megahertz base system. As you can see, we can still see the deeper targets, although they are a little bit weaker. But now the GPR also picks up many shallower objects in the 20 to 30 centimeter range. Finally, we see that when we move to 1000 megahertz, the 5 targets are a lot weaker, the result of the higher frequency being attenuated by the ground. On the other hand, we see a ton, perhaps too many, shallow hyperbolas. Remember that the GPR will pick up any material change. So the majority of these shallow hyperbolas will probably be rocks, debris, or tree roots. The moral of the story is to ensure that you have the right frequency for the task at hand. Okay, so now that we know the basics, let's confront the biggest myth in GPR, which I'm sure many of you have heard over the years. GPR doesn't work in my area because of the clay soil. What it should say is that GPR penetration depth is limited because of the clay soil. Okay? For example, in the Toronto area where I live, there is a fair amount of clay. GPR penetration is limited to approximately 5 feet on average. So what does this mean for a utility locator? Well, GPR can still find gas, electric, telecom, and irrigation lines, to name a few. It usually can't find water, which is buried a little bit deeper below the frost line, or sewers, which are usually around 8 feet deep. So does GPR work in my area where there is clay? Sure it does, but it's important to understand the limitations of what it can and can't find. So if you're not blessed to live in Florida, where GPR penetration is excellent, and the weather ain't too shabby either, let's look at how we can handle challenging survey conditions. This can be broken down into two parts, procedural and viewing. So procedural is what you would do in the field, and viewing data is how you can enhance it on the screen. So remember that GPR reflects off many objects in the ground, rocks, tree roots, debris, just to name a few. When you collect a single line of data and you see a hyperbola, how do you know it's a pipe and not a rock? You need to check to determine linearity. So you do this by collecting parallel lines of data, moving in a zigzag pattern over the ground. As you're doing this, you're looking for hyperbolas that are at a similar depth and have a similar shape or characteristic on each line. So here we see 5 lines, parallel lines that were collected in a zigzag pattern. In general, don't give up if one transect doesn't show anything. Keep persevering by collecting parallel lines. Put paint or flags on the ground and then see if they line up to determine if you have a pipe. Another tactic is to indirectly look for the evidence of the pipe, or what we call the effect of trenching. So remember that when a trench is dug and a pipe is dropped in, the trench is often backfilled with a different material, typically gravel. The evidence of trenching shows up as an X pattern, where the ground strata has been broken. The X pattern is the GPR picking up the walls of the trench, as seen below. While we do see the utility in this example, there are times that the GPR will not see the utility directly, but will pick up the trench walls. So no one digs a trench for nothing. So if you see the trench walls, there's a good chance that even if you don't see the utility directly, there's still something down there. Now sometimes a utility locator is asked to locate a single pipe. At other times, they need to locate all the pipes in an area, including abandoned or capped off ones. And maybe there are just too many targets showing up, and we have no idea what their orientation is. So in the image below, we put dots or field interpretations on the hyperbolas that we crossed. This line scan shows 13 different hyperbolas or objects in a 30-foot long run, which is not very long, really. So to make sense of a congested area, as we've shown here, it is recommended to do a grid scan. Now, a grid scan involves laying out a rectangular survey grid with appropriately spaced lines. You can think of a grid scan as a series of organized line scans. And collecting a grid scan forces you to cover every square foot of the area you are interested in. So in theory, you should not miss anything. Most manufacturers allow grid collection on their systems. On sensors and software's equipment, the grid collection screen looks like the following. The user is easily guided through grid setup and the data collection. Once the data has been collected over the grid, the data is processed in the field to create depth slices. Depth slicing produces a series of 2D map images of GPR data. In this case, we have a grid that's about 22 feet by 21 feet. When locating in an area with many utilities, depth slicing is a powerful way of looking for linear subsurface features. Now, as this video shows, depth slices are viewed like peeling off the layers of an onion, slicing deeper into the subsurface a few inches at a time, looking for linear responses, which are typical of pipes. While collecting grids can certainly help, there are naturally some objections to collecting grids. Keep in mind, the data collection software is very flexible and doesn't require every grid line to be collected. It even allows you to work around obstacles in your survey area. However, the biggest objection we hear is the time involved in laying out a grid. Another option is to collect a grid without laying out a formal grid. Sounds a bit contradictory, right? Let me explain. We call these pseudo-grids, and it relies on having an accurate GPS for positioning rather than using the grid markings on the ground for positioning. If your GPR has an accurate GPS and definitely sub-meter accuracy, and you're working in an open area with lots of sky visible, you can generate depth slices by simply walking back and forth with the GPR system. Cover the area by collecting closely spaced lines, ideally the width of your GPR system, as if you're cutting the grass. Here we can see that someone wandered back and forth around this field with zigzags and various line spacings. Once this was done, the data was processed into depth slices in the Echo Project PC software. While the image that you're looking at has some gaps where the user didn't collect data, the interpolation routine actually works pretty well. And we can see two utilities at this depth slice. There's one over here, and there's one running this way. And we get this result for a fraction of the time involved in setting up and collecting a formal grid. Remember, the key is having an accurate GPS with good visibility of the sky and collecting closely spaced lines. Now that we've covered some tips for field operation, let's look at what we can do on the screen. One of the most important parameters is to ensure that the gain is set properly. The gain amplifies received signals, much like the volume on a radio, and is important for bringing out weaker signals at depth. The image you're looking at right now doesn't have enough gain. So let's turn the gain a little bit higher. By doing that, we can see a slightly better image. On the right, this image has the best gain. In fact, we see a hyperbolic response that was not visible or barely visible in the previous two images. The snowy signals at the bottom represent the background radio noise. Now the gain should be high enough that we see this background noise without overgaining it to the point that the data is hard to interpret. Another setting is the background subtraction filter. This filter is used to eliminate flat line reflectors to emphasize hyperbolas. With the filter off, we can see some flat line reflections, including the direct air and ground wave at the top of the cross-section. By turning the filter on, we can see hyperbolic responses. This filter can also be used to assist with shallow hyperbolic responses, which could be masked by the direct air and ground wave. It's very important for utility locators to recognize when lack of GPR penetration is the issue. In some cases, this is very easy to do. For example, if the utility is known to be about 10 feet deep and the depth of GPR penetration in the area is nowhere close to 10 feet, say 4 feet, there is nothing that can be done to suddenly see 2.5 times deeper with the GPR. When a utility is deeper than the maximum depth range of the GPR, a different locating technique must be used. As we all know, there is no one technology that can do everything. GPR complements electromagnetic technologies very well, and by these I mean the traditional pipe and cable locators. The scenarios below illustrate when electromagnetic methods might be the better choice. Most notably, when you are looking for a single metallic utility that you can put a signal on. Now, GPR is more suitable when you are looking for metallic and non-metallic utilities without tracer wire. There is no other way to find the latter. And please don't say witching rods. GPR can find more objects in a single survey line than any other method. This is because GPR will pick up all objects, even abandoned ones or capped ones that may have been left off of recent drawings. A powerful feature of GPR is being able to produce repeatable visual records. These can be used for archiving, integrated into CAD drawings, overlaid onto Google Earth, or used for writing reports. There are other buried objects related to utilities that might require locating from time to time. These include underground storage tanks, buried manhole covers, and splice pits, all of which can be located with GPR. Finding buried valves can also be done, but it requires the operator to traverse the length of the pipe rather than crossing it perpendicularly like we usually do. If crossing right over the buried valve, it will show up as a shallower reflection. So we know that GPR can easily locate the position and depth of a pipe, though the majority of utility locators will just note the surface position and not give depth unless they are required to. So to round out the topic of what GPR can and cannot do, there are a few situations I'd like to talk about. So the first is determining pipe diameter. When the GPR wave hits a non-metallic pipe, I'm going to play this animation again here, some of the energy is reflected back from the top of the pipe, while the remaining energy travels through the pipe and may reflect off the bottom. If this happens, you may be able to determine the pipe diameter if you can clearly see the reflection from the bottom of the pipe and you know what the pipe is filled with, usually air or water. And it has to be completely filled. So if it's water, it has to be completely filled, not partially filled. The calculations involved are not that difficult, but outside the scope of this webinar. But for those of you that are interested, this is explained in detail in one of our other pre-recorded webinars entitled The Basics of Interpreting GPR Data Part 2, which was recorded by my colleague Greg Johnston. Now be aware of the following things that GPR cannot do. Okay, GPR cannot determine what material the pipe is made of, meaning if it's PVC, terracotta, or asbestos concrete. It cannot determine the condition of the pipe, so if it's broken or if the pipe is cracked or corroded. Now let's look at a couple of case studies. In this example, the client needed to locate utilities buried under a roadway. They scanned an area about 1 kilometer long, and most of the utilities were located with pipe and cable locators, but about 30% of them could not be found. So the GPR was brought in. For this project, they used a Noggin smart card with a center frequency of 250 megahertz and an external GPS. Now the image below shows a small section of the data that was collected, but it's a really great example of seeing a utility in a trench. We can even see some construction layering at the top. After several lines of data were collected, depth slices were generated to visualize the results. This one, at 7 feet deep, shows the utility in red crossing the roadway. So this was pretty much in the width of a road, a few lanes that were scanned. Now, case study 2 illustrates the use of grid collection to locate all utilities in an area, including abandoned ones, prior to excavation. A grid was laid out, as shown below, with lines spaced every 2 feet in both directions. So on this depth slice, centered at 2 feet, we can see several utilities. In fact, there were so many utilities at different depths, we decided to create an animation to visualize this better. And here's the animation. Note that each slice is about 3 inches thick, as we go from top to bottom and then start at the top again. This was a really cool area. We had a lot of utilities there running in both directions. And it really shows the power of doing a grid scan. So in conclusion, GPR is a valuable tool, but it's not the silver bullet. The key to successfully using GPR for all parties involved is to set realistic expectations. This means service providers need to make sure the end clients understand what GPR is capable of. And this will lead to less mistakes and misconceptions and a greater acceptance of GPR as a valuable tool. Whether you're a GPR veteran or are considering getting into it, I encourage you to visit Sensors and Software's website. There are a tremendous amount of resources available, including newsletters, case studies, training videos, and webinars. As well, please visit NELCA's website to learn more about what they do, as well as their competence standards. On a related note, Sensors and Software is proud to offer a one-day utility locating with GPR course, which has been accredited by NELCA to meet their competence standard for the locating technician using GPR. Seemed like a big mouthful there. Details of upcoming courses are also on Sensors and Software's website. This concludes the webinar for today. I would like to thank you all for your attendance. If you have any questions, please submit them now, and I will stay around for a while to answer them. Or if you have to go, you can always email them to the address shown below. Thanks once again, and have a great day.